Hi everyone, you're watching the 11th lecture of E635 Applied Linear Algebra. This is Debisattam and this happens to be the first module. Now today's lecture marks the beginning of a new chapter completely in this course. It's going to be in stark difference with what we have been doing so far. So far we have been mostly looking at linear equations, yeah, and vector spaces and operators in those vector spaces or transformations in those vector spaces. But now we're going to be concentrating more on these linear transformations, especially linear transformations of the kind which operate on the same vector space. I mean, it's a map between map from the vector space to itself. So square maps, finite dimensional vector spaces. And what we're going to learn is how to rip apart those linear operators as much as we can so that we can bring out all possible informations that are hidden within that linear operator, right? So the starting point would be eigenvalues, eigenvectors, yeah, and then we'll see that there's this general idea which is called invariant subspaces, right? And then from there we'll see the more general idea of canonical forms of such linear operators. Okay, so without further ado, let's start with the proceedings. For that, I'll have to share my screen. Yeah. Okay, so the originating problem here for the idea of eigenvalues and eigenvectors is the problem of the more fundamental problem of trying to solve dynamical equations for linear dynamical systems. Now, what we mean by linear dynamical systems, let me explain. So what we have here is something like this. So suppose this is our lecture 11. Yeah. So suppose we are in Rn, okay, and we look at a typical vector x1, xn, n tuple, and we're going to call it x. Now let's assume that this x is such that it's actually a function of time, right? So this is xt. So that means each of these entries are actually functions of time, right? And now suppose we have an equation, because it's a function of time, I can just take pointwise derivative dx dt, and suppose this is equal to a times x, and suppose this is true for all t, where A happens to be a matrix, a square matrix of size n cross n. So this is the typical example of an nth order differential equation, right? Ordinary differential equation with linear with constant coefficients, linear ODE with constant coefficients. All right. Compare this with the situation when these the time axis is let's say it's a discrete. So time axis has been discretized. In that scenario, this x is going to be something that is defined for every k, where k belongs to the set of natural numbers, and the equation that governs this system is the following: that x at the k plus first instant is given by a times x at the kth instant. Yeah. What we mean by saying that we would like to solve this equation is, so this is discrete, and this of course is continuous. What we mean by solving, by a solution, we mean for the continuous case, a function xt that satisfies this equation. Right? Find out an xt that satisfies this equation. Xt that satisfies equation number 1. And for the discrete case, likewise, find out an xk, which is a sequence now that satisfies this equation, which is equation number 2. That satisfies equation 2. That's it. Now the question is, how do we get these solutions? Yeah, to put things to perspective, let us try and see what problems we expect. And to keep our life easier, we're going to consider n to be equal to 2. This is perhaps the easiest case beyond n equal to 1. And n equal to 1 is absolutely simple, you know. So before we start n equal to 2, let us look at n equal to 1. For n equal to 1, by the way, this is really tedious to write dx dt all the time. So the shorthand that we use is dx dt. Instead of writing dx dt all the time, we're going to write it as x dot. Right? Yeah. So here we have x dot equals ax, where a is just a scalar, right? Because it's n equal to 1. And also xt for all time is also just a real number. So this is just a real function. So x is in fact a function from R to R, right? And we already know how to solve this equation. This is dx by x a dt, integrating from x at 0 to x at t, dx by x equals a integral from 0 to t dt. Yeah, you have to write this as tau, but that's okay, I think. I mean, I'm sure you understand what's going on here. D tau, and this is ln x t, yeah, minus ln x0 equals at, which tells us that ln xt by x0 is equal to at, which tells us that xt is e to the power at into x0. That's the solution. Yeah, right. On the other hand, if you have the discrete case, then that's xk plus 1. Okay, x at k plus 1 equals a xk. And of course, we know that this is, a is just a scalar here. This is a. So it just follows that x1 is a times x0. x2 is a times x1, which is the same as a squared times x0. And if you keep on doing this, you're going to find out that xk is nothing but a to the power k x0. That's the solution. So for n equal to 1 case, it's absolutely simple. The question is, what would happen when it is not so, when n is bigger than 1? So let us look at the next possible case, that is n is equal to 2. And we're going to concentrate on the continuous situation here. So what's going to happen here? Notice that now, because n is equal to 2, I have x1 and x2, two components, and the differential equation is going to look like a11, a12, a21, a22, x1, x2. Expanding, what we're going to get here is x1 dot equals a11 x1 plus a12 x2, and similarly x2 dot is equal to a21x1 plus a22x2. And the question is, how do we solve this? Actually, if you think about this carefully, this is actually a chicken and egg problem. Why so? Well, x1 dot has x1 as well as x2, this variable. So unless I know what x2 is, I will not be able to solve this. Compare this with the earlier situation. We didn't have multiple variables, we just had only one variable x, and that's why we could do this trick. But here we can't. Yeah. But in order to get x2, the equation that x2 satisfies, which is this one, that involves x1. Yeah. So I need x2 to solve for x1, and in turn I need x1 to solve for x2. So it's a chicken and egg problem. Which one do you solve first? Yeah, neither. That's a problem. That's the problem of a coupled differential equation. The problem is happening precisely because of the coupling. It's a coupled differential equation. Yeah, by coupling we mean the presence of these variables. Right. Now, if you think about this just for a little while and assume that the couplings are not there. So for the special case, suppose the couplings are not there. What would happen then? Well, suppose that the equation is x1 dot equals a11 x1, and the second equation is x2 dot equals a22 x2. This equation involves only x1, this equation involves only x2, and I could just use my earlier knowledge and say that this is just a scalar situation, and it's going to be e to the power a11t into x10, and the second would be x2t equals e to the power a22t x20. That's it. Although it's a second order equation, but it's actually a first order equation in disguise. I mean, just to complicate things, I've written them together. I could just have written them separately without any issue. Geometrically, it would look something like this. So you see, if this is my x1, x2 axis, x1, x2, and suppose this is my initial point, x at t equal to 0. This has two components. This is x1 at 0. This is x2 at 0. This with x1 equal to 0, there will be an evaluation and it will remain here for all time. With x2 equal to x2 0, we'll have a solution which will remain here forever because this is the formula. Yeah, and then for a particular time, let's say t equal to capital T, suppose x1 capital T is here and x2 capital T, let's say, is here. Then x would be given by this linear combination, which is this point. Yeah, is that all right? And similarly, if this is at another point, then together it will be this point, like that. And you can check that the solution would be something like this. This, of course, with the understanding that a11 is less than 0 and a22 also is less than 0. That is, these two numbers are less than 0, so that x1 is decreasing exponentially, x2 is also decreasing exponentially. And this is the solution set. In fact, in this scenario, if it so happens that the dynamics in the x1 direction is faster than the dynamics in this direction, which means a11 magnitude is bigger than a22 magnitude, in that scenario, the whole solution is going to look like x1, x2. In the x1, x2 plane, it's going to look like, so x is faster, right? So it's going to look like this. Such things are called phase portraits. Those who have done or are doing nonlinear dynamical systems course E613, they would know that this is such a thing is called a stable node. Yeah, it's called a stable node. Yeah, so easy. And the reason it was easy because the equations were decoupled. Right? The question that we are trying to answer here is that if the system to start with was not decoupled, can it be made decoupled? So, can a coupled system of equations be made decoupled? Yeah. At this point, perhaps you can take one immediate attention problem. Draw the phase portraits when A11 magnitude is less than A22 magnitude. Yeah. Yeah. So we are face to face with this question. Let us try and see what happens to this particular case when n is equal to 2. Can we convert this into a this coupled system into a decoupled one? Sorry. Now, so suppose suppose what we do is, let's say, a linear change of variables. Now, what do we mean by that? Say v1 and v2, let's say, are two vectors in in R2 such that now we're going to make some assumptions, yeah? And these are pretty strong assumptions, so I'm going to use red color for that, and we'll have a lot more to say about these assumptions throughout the rest of this course. First one, say v1 and v2, this set is linearly independent, so of course non-zero. There will be more assumptions added to this list as we go along. Now, with this assumption, you see this vector that we had x1, x2, the general vector at some time t, this can be written, so let me keep the argument t. This can be written as a linear combination of v1 and v2 because it's linearly independent. So it's a basis now, right, for R2. So I can write this as some unknown variable z1t into v1 plus another unknown variable z2t times v2. These are the coefficients, yeah. z1t is a real number, it's a real coefficient. Z2t is also another coefficient. So the fact that any vector in R2 can be written as a linear combination, unique linear combination of v1, v2, tells me that such I can find such z1t and z2t. Yeah, is that all right? What happens when I take the derivative? Well, I have x1 dot to be equal to z1 dot, that's the only function of time. V1 is not a function of time, so it remains as it is, and z2 dot t times v2. Similarly, we'll have x2 dot t equals z1, oh, x1 dot, this is together, yeah, because v1, yeah, right. Yeah, we'll have something like this, right? However, at the same time, I know that this satisfies the equation that this is equal to a times x, which put together here means that this is a times z1t v1 plus z2t v2. But notice that these are scalars, so this a will just distribute over these, and so we'll have z1t times a times v1 plus z2t times a times v2. Now we add one more assumption to the to our list. We don't know whether this is possible or not, but let us just assume that a times v1 is equal to some lambda 1 times v1, and a times v2 is equal to some lambda 2 times v2, where lambda 1 and lambda 2 are some real numbers, right? This is assumption, by the way, and red color assumption, so we don't know whether this is going to be true always or not, but let us say that this is the situation, and we'll see what happens in this scenario. If that's the situation, then under the assumption, we'll have this term equal to z1, okay, let me write it properly, lambda 1, which is a constant scalar, times z1t into v1 plus lambda 2 z2t times v2. Now we combine these two things. This must be equal to this. So together, if we take them all on one side, we're going to have this quantity times v1 plus this quantity times v2 going to 0. But what did we assume? We had assumed that these two are linearly independent. So this linear combination goes to 0, would mean z1 dot at all time t must be equal to lambda 1 times z1t, and z2 dot t must be z2t for all time. This is because this set has been assumed to be linearly independent. But now this is a decoupled system of equations, and trust me, if I solve for z1 z2, I actually know what x1 x2 is. Indeed, the solution here is z1t is equal to e to the power lambda 1 t into z1 0, and z2t is equal to e to the power lambda 2 t z2 0, which tells me that the solution x1t x2t is going to be nothing but e to the power lambda 1, sorry, e to the power lambda 1 t into z1 0, which is a scalar, into v1 the vector, plus e to the power lambda 2 t z2 0 v2. Yeah, is that all right? Which is the same as in matrix vector notation. I could just go ahead and write this thing as v1 v2 written side by side in between the diagonal matrix like this and z1 0 z2 0. Yeah. However, we also know that x1 x2 at all time is equal to v1 v2 z1t z2t, which then tells us that z1 0 z2, okay, z1t z2t is going to be v1 v2 inverse. Such an inverse exists because v and v2 are linearly independent. x1t x2t. Yeah, is that all right? So in particular, z1 0 z2 0 is equal to v1 v2 inverse x1 0 x2 0, which then putting this in equation star, putting this in star, we get the solution x1t, x2t is given by v1, v2, the matrix, e to the power lambda 1 t 0 0, e to the power lambda 2 t, the matrix, then v1, v2 inverse x10, x20. That's it. That's the solution. Yeah, that's the expression for the solution. Now, geometrically, what this means is that, so if we call this matrix T, which happens to be v1, v2, then the solution is xt is equal to T, then this matrix, this diagonal matrix, T inverse into x0. This is the solution. So all important matrix T, T inverse. Yeah. Well, geometrically, what does this mean? Well, you see, notice carefully. What we are saying is that v1, v2 is linearly independent. So in fact, if I choose basis, a new basis v1, v2 for my R2, this is the new basis B. Under this basis, the vector x at all time, under this basis, this representation is what? This representation, okay, remember that x is equal to z1 v1 plus z2 v2 all time, right? I'm just omitting that the argument t, but it's understandable that it's also for all time. So if this is the expression for x, then x's representation under this new basis is nothing but the vector z1 z2, which let us call z. And in this situation, z dot is given by lambda 1 0 0 lambda 2 into z. Yeah, this is the equation. This is the decoupled equation that it follows. And we know that this matrix here, what is this matrix, by the way? Well, if you see it, so notice what equation we have. We have t times z is equal to x. Yeah. So x dot must be equal to t times z dot, which is the same as t times, yeah, it's t times z dot, but that is the same as ax, but this x is once again t in x is t times z. So then from here it follows that z dot is equal to t inverse at into z, and we all know that this t inverse at, from what we have learned before, that this t inverse at is nothing but the, so this we call a nu. So a nu is the matrix representation of the operator given by a, x maps to ax. This is a linear operator. This linear operator, when represented in the basis, nu is the matrix representation of this operator under the new basis B. So A is the representation of the linear operator in the standard basis. Yeah, that's the linear operator. And when I do this change of coordinates, I represent the vectors, all the vectors in this new z coordinates. In that new coordinate system, A is represented by A nu, right? So geometrically, it's going to look something like this. First, we have x plane, which is these two axes, x1, x2. We have z plane, where we have once again two axes, z1, z2. How are they related? Take any vector z here, that when gets multiplied by t gives me x. So the relation is x is equal to t times z. What more do we know? We know that what is this t? T is v1, v2 written side by side. So which then tells us that the map is such that E1 gets mapped to V1. So under this T, E1 gets mapped to V1 and E2 gets mapped to V2. That's the map. The opposite direction obviously is T inverse. So under this T inverse mapping, this V1 goes to E1 and V2 goes to E2. And not just that, because these are linear maps, in fact this whole axis spanned by V1 goes to this Z1 axis, and this whole axis spanned by V2 goes to the whole of Z2 axis, right? Now in this plane, if the dynamics is, let's say, a stable node, then it's going to look like this. Yeah, like before, as we have seen. When it gets mapped here, it's going to look like a distorted version of the same. A distorted version of the same, like this. So geometrically, we're just doing a change of coordinates. And if the two assumptions hold, the ones that we have written here, if we succeed in finding vectors like this, v1, v2, then with the help of this v1, v2, I can do this linear change of coordinates so that in the new coordinate system, the equation becomes a diagonal equation. Yeah. So I hope the geometry is also understandable. Okay. So then in that situation, our question boils down to the following. Question, say 1. The question is, so given a matrix A, say for the time being, okay, let's do it for general. Nothing's going to change much. Rn is an n cross n matrix with real entries. This is given. Question is, does there exist a T matrix, yeah, which is also in Rn cross n, T invertible, such that T inverse AT, which we are calling A nu, is diagonal? This is the question. Does there exist a invertible matrix T such that it's diagonal? Right? That is precisely what is happening. That is what diagonalizing this differential equation really means. Decoupling the differential equation really means. Notice that this question Q1 is in fact equivalent to asking this question Q2, which is such that, so what is this T inverse AT? T inverse AT is actually representation of A in the new basis, where the new basis is nothing but given by the columns of in the same order, you know, in the so the columns taken in the order from left to right. If that is an ordered basis, that is taken as the ordered basis, then this T inverse AT or A nu is nothing but the representation of A under this new ordered basis. So then the same question can be posed as, for a linear map like this, with V being a finite dimensional vector space. So did I write? equal to n less than infinity, a finite dimensional vector space, does there exist a basis B such that phi's representation in this basis is a diagonal matrix? As I have just explained, Q1 and Q2 are actually equivalent questions. So we're going to use this more sophisticated language than this one, because this is matrix theoretic, and this follows, Q1 follows from Q2, but Q2 is much more general. It doesn't require us to start with, we don't have to see vectors as tuples of numbers. So can we do this? Yeah. Now we'll see the simplest answer to this question, and then we will try to see how the question becomes more and more complicated. So we'll answer this question Q2, but we'll not be able to answer this in full generality. We're going to see a special case of this where there is ready-made answer. What is that? So partial answer to Q2. Suppose there exists lambda 1 dot 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 up to lambda n real numbers, and v1 up to vn vectors in the vector space V, such that this set is linearly independent. So these are non-zero vectors, non-repeated, that is distinct vectors, and non-zero. So non-zero, and moreover, suppose they are linearly independent, then linearly independent with the property linearly independent such that this operator that I have, phi's action on Vi produces lambda I times Vi. Okay. Suppose this is my basis because it's linearly independent. Then notice that phi's representation in this basis B is going to be what? It's going to be, recall, how do we represent a matrix under a basis? So we look at the first basis vector V1 and see how phi V1 is represented in the basis. What is the representation of phi V1 in this basis? So the first column is phi acting on V1, its representation in the basis. The second column is phi V2, its representation on the basis, in the basis, and dot 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 phi Vn in its representation in the basis. Right? What is this representation? What is phi V1? Phi V1 is lambda 1 times V1. So the linear combination is lambda 1 times V1 and 0 times V2, 0 times V3, so on up to 0 times Vn. For the second guy, this is phi V2 is lambda 2 V2. So 0 times V1, lambda 2 times V2, 0 times V3, and so on up to 0 times Vn. Third vector, 0, 0, lambda 3, and all zeros. This trend continues. Finally, we'll have 0, 0, 0, and this guy will be lambda n. Diagonal matrix. So existence of such vectors that satisfy this property solves the problem for Q2, that if such a thing exists, then Q2 is there exists a basis. Q2 has an answer, right? So these vectors are special. The question is, can we find these vectors? When is there a guarantee that such vectors will exist? It appears that that should be a property of this linear operator, right? Based on the linear operator, we should be able to figure out whether such things exist or not. Those who have seen a little bit of linear algebra before would immediately recognize that this is eigenvalue eigenvector equation. The question is, would there be n linearly independent eigenvectors? Yeah. This is the question that we are going to answer in the second module. Yeah. So before we go to the second module, I would like you guys to solve these two problems. Immediate attention problem, namely, say first one is, suppose I have a matrix A which is given by say 0, 1, and suppose we have -2, -3, yeah, like this. Then find v1, v2 such that v1, v2 inverse A v1, v2 is diagonal. Yeah, so we are directly diagonalizing this. Immediate attention problem 2 would be this process that I have described here. This I did for question 2. Using the same idea, find out question 1 form of this one. So, okay, Q1 analog of Q1 analog of Q2. Work out Q1 analog of Q2. This is your second immediate attention problem. Solve these two immediate attention problems, or at least try them. Make an attempt. If you can't, then we should discuss this during the live session. Yeah, so do that, and then let's meet in the other side of the break. Okay.